Imagine you've successfully developed a process in a 20-liter laboratory reactor. The reaction proceeds smoothly. Mixing is excellent. The product meets every quality specification. Now it's time to manufacture the same product in a 20 kiloliter production reactor. To keep everything the same, you install the same agitator, and you also keep the speed at 100 RPM. Everything should work exactly the same, right? But the first commercial batch doesn't. The reaction takes longer. Temperature becomes non-uniform. Mixing is no longer the same. What went wrong? After all, 100 RPM is still 100 RPM. Isn't it? By the end of this episode, you'll understand why experienced process engineers almost never scale up agitation using RPM alone, and how they decide what to preserve instead. One of the biggest misconceptions in agitation scale-up is believing that keeping the same RPM will produce the same mixing. But RPM simply tells us how fast the shaft rotates. It doesn't tell us how much liquid is circulating. It doesn't tell us how much mixing energy is entering the liquid. And it certainly doesn't guarantee the same process performance across different reactor sizes. That's why experienced process engineers rarely scale up agitation based on RPM alone. When reactor size increases, the entire mixing environment changes. The liquid now has to travel much farther. The impeller must circulate a much larger volume of liquid. Heat removal changes. Gas dispersion changes. And if solids are present, keeping them suspended becomes more difficult. The chemistry remains the same, but the physics of mixing changes completely. If RPM isn't the answer, then what should engineers preserve? Should we preserve the same mixing energy? Should we preserve the same shear? Or should we focus on uniform mixing? What if the process contains solid particles? Or depends on a particular flow pattern? Clearly, simply keeping the same RPM isn't enough. The real question is, what does your process actually need? This is perhaps the most important lesson in agitation scale-up. There is no universal rule that works for every process. A hydrogenation reaction doesn't behave like a crystallization process. A blending operation has completely different objectives from a solid suspension process. That's why experienced engineers never begin with RPM. They begin by understanding what the process is trying to achieve. This is perhaps the most important lesson in agitation scale-up. There is no universal rule that works for every process. A hydrogenation reaction doesn't behave like a crystallization process. A blending operation has completely different objectives from a solid suspension process. That's why experienced engineers never begin with RPM. They begin by understanding what the process is trying to achieve. We now know that preserving RPM isn't the goal. But what exactly do experienced engineers preserve? Let's begin with our first engineering tool. Tip speed. Imagine two impellers rotating at exactly 100 RPM. One has a diameter of 0.2 meters. The other has a diameter of 2 meters. Now imagine placing a small paint mark on the tip of each impeller. After one complete revolution, both impellers have rotated exactly once. But the larger impeller tip has traveled a much longer distance. That means its tip is moving much faster through the liquid. This speed at the outer edge of the impeller is called tip speed. Instead of asking, how fast is the shaft rotating? Tip speed asks, how fast is the liquid being sheared? Our second engineering tool is power per unit volume, or simply PV. Instead of asking, how fast is the impeller rotating? PV asks, how much mixing energy is actually entering the liquid? Think about stirring a cup of tea. Now imagine stirring a bucket filled with thick syrup. The effort required is completely different. In a reactor, the same idea applies. The impeller transfers mechanical energy into the liquid. That energy creates circulation, turbulence, and ultimately, mixing. The more energy transferred into each unit volume, the stronger the mixing becomes. Sometimes, our objective isn't creating high shear. It isn't maximizing mixing energy. We simply want the entire reactor to become uniform. That's where blend time becomes important. Imagine adding a blue dye into clear water. Initially, only one region becomes blue. As the impeller continues to rotate, the dye spreads throughout the vessel. Eventually, every point inside the reactor reaches the same concentration. That time is called the blend time. Two other engineering tools are also widely used during agitation scale-up. The first is the Reynolds number. It helps engineers understand the flow regime inside the reactor. Is the liquid flowing smoothly, or is it highly turbulent? The second is NJS, or the just suspended speed. It is the minimum agitator speed required to keep all solid particles suspended without settling at the bottom. We'll explore both of these in much greater detail in the next episode, where we'll perform actual scale-up calculations. Now we've learned the engineering tools. But knowing the tools is only half the job. The real engineering challenge is choosing the right one. Don't try to memorize this diagram. Instead, use it as a way of thinking. Every successful agitation scale-up begins with one simple question. What controls my process? If heat or mass transfer controls the process, think P. V. If product quality depends on shear, think tip speed. If achieving a uniform composition is your priority, think blend time. If solids must remain suspended, think NJS. And if you are evaluating the flow regime, think Reynolds number. This is exactly how experienced process engineers approach agitation scale-up. Understanding these engineering tools is essential. But in a real manufacturing plant, engineers don't choose a scale-up criterion by memorizing a diagram. They choose it by solving real process problems. So let's step into the role of a process engineer and see how these decisions are made in actual manufacturing scenarios. Imagine you are scaling up a hydrogenation reaction. The chemistry hasn't changed. The catalyst is the same. The reactor temperature is the same. Yet after scale-up, the production team reports that the batch is taking almost 2 hours longer to finish. Which criterion would you preserve? The same RPM? The same tip speed? Or the same power per unit volume? Take a moment and think. Pause for -3 seconds. The correct answer is power per unit volume. Why? Because in many hydrogenation reactions, the reaction rate depends on gas-liquid mass transfer. Hydrogen must disperse efficiently into the liquid before it can react. By preserving mixing energy, engineers help maintain gas dispersion and reaction performance. Now let's consider a crystallization process. After scale-up, operators report that filtration suddenly takes much longer. Quality control also finds that the crystals are significantly smaller than expected. What should you preserve? RPM, power per unit volume, or tip speed? Take a moment and think. Pause. The correct answer is tip speed. The smaller crystals tell us something important. They're being exposed to too much shear. The issue isn't poor mixing. It's crystal breakage. By controlling tip speed, engineers limit shear and protect crystal growth. Let's look at another process. During production, operators notice catalyst settling at the bottom of the reactor. Once particles settle, the available surface area decreases. Reaction performance becomes inconsistent. What should you preserve? RPM, power per unit volume, or NJS? Take a moment and think. Pause. The correct answer is NJS. NJS is the minimum agitator speed required to keep all particles just suspended. If agitation drops below this value, solids begin to settle. And once settling starts, process performance begins to suffer. Finally, consider a simple blending operation. After scale-up, quality control collects samples from different locations inside the reactor. Surprisingly, each sample shows a different pH. The reactor isn't becoming uniform. What should you preserve? RPM, tip speed, or blend time? Take a moment and think. Pause. The correct answer is blend time. In blending operations, our objective isn't maximum shear. It isn't maximum turbulence. Our objective is uniform composition throughout the vessel. And that's exactly what blend time measures. Did you notice something? In every example, the reactor became larger. But the engineering decision was different. Why? Because each process had a different objective. Hydrogenation depended on efficient mass transfer. Crystallization depended on controlled shear. Blending depended on achieving uniformity. And solid suspension depended on keeping particles off the bottom. The reactor changed. The process changed. So the scale-up criterion changed as well. That's exactly how experienced process engineers think. We've solved 4 different engineering challenges. And although each process was different, they all followed the same decision-making approach. So before we end, Let's summarize the most important lesson from today's episode. Throughout this episode, we've discussed several engineering tools: tip speed, power per unit volume, blend time, Reynolds number, and NJS. It's easy to think that successful scale-up is simply about choosing the right equation. But experienced process engineers think differently. They begin with one simple question: what controls my process? If the answer is mass transfer, preserve mixing energy. If it's shear, protect tip speed. If it's blending, focus on blend time. The engineering tool changes because the process objective changes. Here's the biggest takeaway from today's episode. Many scale-up failures happen because engineers try to preserve the same operating conditions, the same RPM, the same settings, the same numbers. But reactors don't care about numbers. They respond to physics. Successful scale-up isn't about reproducing operating conditions. It's about reproducing process behavior. If heat transfer remains the same, if mass transfer remains the same, if shear remains within limits, if solids remain suspended, then the process has been successfully scaled up. The RPM may change. The impeller size may change. Even the power requirement may change. But the process performance must remain the same. Let's test your engineering thinking one last time. A crystallization process has been scaled up from 50 liters to 5 kiloliters. During production, filtration suddenly takes much longer, and quality control reports much smaller crystals. Which scale-up criterion deserves the highest priority? A. RPM. B. Power per unit volume. C. Tip speed. Or D. Reynolds number. Pause the video, think like a process engineer, and comment your answer below. Pause at -10 seconds. If your answer was tip speed, you're absolutely right. The smaller crystals indicate excessive shear, so protecting tip speed becomes the priority. Let's quickly recap what we've learned today. RPM tells us how fast the shaft rotates, but it doesn't guarantee the same mixing performance. Different processes have different objectives. That's why experienced engineers don't preserve RPM. They preserve process performance. And that's the mindset that leads to successful scale-up. In our next episode, we'll move from engineering concepts to engineering calculations. We'll learn how to calculate the new agitator speed using tip speed, power per unit volume, Reynolds number, and NJS. So if you don't want to miss that episode, make sure you subscribe to PharmaChemE. If you found this video valuable, please give it a thumbs up, share it with your colleagues, and let me know in the comments what topic you'd like to see next. Until then, keep learning, keep solving problems, and remember, engineering isn't about preserving numbers. It's about preserving process performance. I'll see you in the next episode.